Hello, ladies and gentlemen. This is Alice and Beijing. I'm so glad to meet you again at Friday IKX Talks. We connect the world and the universe. I'm so proud of that to tell you today we actually was a holiday in China. It's a big celebration for the Dragon Boat. It's in the memorial of a long term time ago, more than 2,000 or 3,000 years ago. A great poet, name was Qu Yuan. So now sounds like the whole country should go somewhere for celebration for the holiday. But where they are, I saw the numbers online for IKX Talks. I'm proud to tell everyone. Many people would go online for IKX Talks. So welcome everyone from China, from everywhere in the whole world. We actually to have IKX Talks. All this latest result of science and technology to connect the world and the universe. It's a very beautiful day. And today we will have two speakers and one guest, hosters, Paris, to with us. So, but before we go to these wonderful talks, for toward a new area of thinking microfabrication and adding new sense of dimension. So I have one thing to announce. It's for the Mind 2020 Young Scientist Forum. So this will be, the week after next week. I'll be in the early July 7 to 10th. So we have 53, speakers divided into 6 sessions, into 6 days. Into 3 days, 6 sessions. Every day, 2 parallel sessions. The first session, the first day at July 7th will be flexible and soft devices. 9 speakers, all these are assistant professors worldwide, and they will deliver the talks. And in this session, flexible and soft devices. This was session 1 in July 7th. This was session 2. It's for biomedical science and technology. 9 speakers, will talk on this. And the second day is July 8th. We will have advanced micro and nano fabrications. We will have another session is energy harvesting and self-powerful system. In the third day, we'll have sensors actuators for biomedical applications. And another section is advanced micro and nano sensors. So all these 6 sessions, every session we choose the top 2 to win the honor and the title for Young Scientist Award. So we will have the celebration, the ceremony on IKX Talk, the July 10th. In the end part of the talks, it will be this award ceremony. So you will see all these winners. Now this event is free for registration. If you are interested to see, all these young scientists worldwide and their wonderful works, so you are welcome to log in the website and register on time. This is totally free, but you must register. If you didn't register, you are not allowed to attend all these talks. So you just can see the winners on IKX, but you don't know how beautiful they are and what kind of jobs they do. So please register online and please join us to see all these wonderful talks and Mind 2020. That's one advertisement for this event. Why I do that? Because I was a chair for this event, for 4 years. So please join us, to welcome and celebrate all these young scientists worldwide and promote them. So that's the advertisement for the new event will come out in next month. And now come to the today's talk. I say that we have 3 guests here. The 2 speakers with Sheng Xu and Azakan, all from California. Now it's early morning in California, but all of them are ready to give their wonderful talks. Now the first speaker is Sheng Xu. Sheng Xu was from University of California and San Diego. So he's very, excellent, speakers, outstanding speakers. The first time I met him is last April in Phoenix. He won a big title, is MRS, Outstanding Young Scientist Award. That's a super, kind of honors for the young scientist. I saw him give a lecture amazing lecture for thousands of attendees. That time I think I must have shown on my talks. So now the dream come true. And also I have one word here. I'm very proud of Sheng because Sheng was graduated from Peking University. He's our outstanding alumni. So Sheng, now the word is yours. Yeah, please.
Can everybody hear me well? Thank you very much, Professor Zhang, for establishing such a wonderful platform and also giving me this opportunity to expose our research to such a broad audience. It's our great honor and fortune to speak to all of you here today. So this is a brief outline of my talk today. So firstly, I will briefly motivate on our research with the perspective of this soft electronics. You have heard a lot of outstanding presentations in these ICANX talks during the past few weeks. So I'm sure you are very familiar with these wearable, flexible, stretchable electronic devices. So I'm not going to spend too much time. I'm not going to preach to the choir. And the main body of my presentation is going to be focused on how are we going to make these flexible, stretchable electronic devices. I came from a chemistry and materials background and always have a mindset of how to making things, right? How can we make a flexible, stretchable these devices? And I'm going to show you two strategies. One is materials innovation with a focus on this organic, inorganic, hybrid highlight process and share with you some of our recent developments in this area. Some of them have not been published yet, and this is going to be my first time to show you those results. And the second approach is structured design. This is very widely used in the field. I'm going to focus on two recent developments in my group. The first one is this multi-layered stretchable device, and the second is this stretchable ultrasonic device. And finally, briefly summarize. So soft electronics is an emerging field. It has a lot of implications with applications in a broad range of areas. So from this perspective industry, people have already demonstrated these prototypes, such as cell phones, displays, and the smart watches. Those are all like flexible prototypes. They are not like a cartoon or whatever. Those are real devices you can see in like whatever kind of demonstrations or these conference booths. The second, focus is this healthcare area, healthcare sector. So a very famous example is this contact lens manufactured or produced by those Google X some time ago. The goal is to monitor this glucose level in the tear, non-invasively and continuously. Wearable tattoo for monitoring the health status, right? So this is my personal area of interest as well. Smarter surgical tools, instrumented surgical tools to make those passive surgical tools smarter, more functional, highly integrated, do more work, so on and so forth. Soft robotics, this is a big area, big focus. Trying to make those robotic devices mimic the dexterity and adaptability of these animals or humans, right? To achieve like a more sophisticated functions. Soft energy, because all of these electronic device is the soft, flexible, stretchable. So you also need these devices, energy devices in a similar format, right? So this is like the broad implication in a wide range of areas. How can we make this, right? How can we build those devices, from a material perspective? What you're looking at here is a comprehensive review of the approaches people have demonstrated in the literature to make soft electronic devices, particularly stretchable device. My group published a very comprehensive article about 2 years ago trying to summarize all those approaches. And the students did a fantastic job trying to review, I think, around over 2,000 papers in the literature, and eventually started around 600 of them. So the approaches people have demonstrated can be basically grouped into two categories. One is a material strategy, the other one is the structures, right? So I'm not going to go through the details of each one of them, but the key message is this review article is so exhaustive That means it covers almost, I was saying almost, it covers all of these approaches people have already demonstrated in the literature. If you can ever find one approach that people used to make these stretchable devices and not covered in this review article, send me an email, okay? And then I will buy you a dinner or lunch at a restaurant you pick. Okay, so that's the message I send out to this broad audience out there. So there are so many approaches in the literature. What's my interest, right? What's my approach? And I'm going to show you two fundamental interests, in my group. The first one is to reduce the size of these materials to like hundreds of nanometers in dimension. And it turns out that according to this classical mechanics, this is what I learned when I was a postdoc in Professor John Rogers' group. The bending stiffness is linearly proportional to the third power of its physical dimension, right? So I'll give you a simple example. For a tree trunk is very stiff and sturdy, right? But if you make the tree into a piece of paper, then it becomes very flexible. So that's the idea. What you're looking at here on the right-hand side are two examples of this conventional rigid and brittle material. Gallium arsenide and silicon. As you know, when you have a big chunk of those material and you fall them on the ground, then they will break into a million pieces, right? So those are very fragile materials. But when you reduce the dimension of those two materials down to a thickness of around a few hundred nanometers, then it becomes very flexible, right? So those two images represent two typical examples of this controlled buckled nano ribbons. So this is like a single crystal gallium arsenide nano ribbon. This is a single crystal silicon ribbon. The entire piece here is a single crystal monolithic thin film membrane, right? So as you probably know, those two materials forms the backbone of the modern electronics, which means when you open up a electronic device nowadays, it's very difficult for you to find a electronic device that does not have any of this material inside, right? So they are, the basis of our modern industry nowadays. Those two materials are typically grown by those fancy equipment at high temperature, high cost, right? So you have to, somehow buy those materials from a commercial vendor. You cannot grow them, at low cost, at the own lab, at the own place, right? So they are not very widely accessible. So organic, inorganic, hybrid highlighter perovskites is an emerging material, and it shows comparable high performance electronic, optoelectronic, and the transport properties in comparison with those gallium arsenide and silicon materials, right? A big advantage of this hybrid highlighter perovskite is that it can be grown in solution at a low cost. You can grow those materials in your lab in beakers, just by some chemical substance, organic salts, right, and inorganic salts, and then mix them and then grow in your own hood, right? So this can be manufactured at a large scale. And if you do a literature survey, you'll find out that most of the people have been focusing on either polycrystal, these perovskites, or single crystal bulk materials. And those materials, those form factors are great. Say, for example, these polycrystals can demonstrate outstanding performance in comparison to those silicon devices and gallium arsenides. These bulk single crystals are good for starting some fundamental physical transport behaviors, but they are hardly useful for integrating into high performance device. Polycrystals have those green boundaries and defects. So, those free carriers will recombine, will annihilate before they, get collected, right? So the performance will degrade. And for bulk large single crystal, it's very difficult for them to be integrated onto these devices, which is mostly based on thin films. So far, there have been no epitaxial single crystal thin films based on those hybrid highlighter perovskites. And the challenges are twofold. The first thing is, it's very difficult to find a substrate that have an epitaxial relationship with those hybrid highlighted perovskites. As in the case of silicon and gallium arsenide, you can find a very large range of those substrates to grow those materials, right? This is the first fold challenge. The second challenge is that this organic, inorganic highlighted perovskite is very sensitive to water. That means if you immerse them in any solvents or water-containing solvents or these etchants or solutions, they will decompose very quickly into lead, highlights, and some volatile organic compounds, right? Then that means they are not compatible with those conventional microfabrication, lithography-based microfabrication. So those are the twofold challenges that prevents people from making those epitaxial single crystal thin film of this material. So my group looked into this area and tried to tackle those challenges, and we tried a bunch of different substrates. Eventually, we can grow some materials on some substrates, but they are all van der Waals force-based interaction. That means those crystals have a very weak bonding with the substrate, and that weak bonding prevents those material from long-range order. So on a large scale, they are part crystal, but they have those large domains, right? So they are still not perfect. Then one of my graduate students came up with this fantastic idea saying that why don't we use those large single crystal perovskite as the substrate itself, right? So if you use the material itself as a substrate, then of course you can grow those single crystals, material on top of it. Then how can we control the growth of this single crystal thin film of this perovskite on top of itself, on top of this large single crystal bulk, material? We have to use photolithography. And as I just said, this material is very sensitive to water. How can we prevent this material from decomposition, right? So that's what I learned from Professor John Rogers when I was a postdoc in his group. And the trick we played was that we coat a layer of very hermetic polymer material on this bulk single crystal substrate to protect it from decomposition in water. And that material we use is Pyrene C. Why is Pyrene C? Because it was like very widely used in the battery field. It is very hermetic. It can prevent those lithium metal and those organic solvent from penetration of those organic from this penetration of these water molecules and oxygen molecules to react from them, right? So this material is a fantastic barrier for this moisture and oxygen. And after we protected this perovskite using a very hermetic layer of Pyrene C, then we can start to do all kinds of photolithography, microfabrication on top of it. And this is a brief, oversimplified flowchart of the process. And after we open up the holes using this wet etching, so on and so forth, the final step is to use this gas phase, dry etch, to remove this Pyrene C to expose those bulk single crystal perovskite. And of course, it's very difficult to control the etching step to stop at the surface of this perovskite. You will have a little bit of over etch in this case and form some part crystal. That does not matter. You can just use the solvent to dissolve this part crystal, and that will expose very nice, clean, fresh single crystal surface. And you can use that to grow those single crystal perovskite in one. So this is the idea, the design. And after a few months of trial and error, my student eventually were successful in growing those beautiful single crystal layers. So what you're looking at here are some SEM images showing these typical structures we can grow. As you can see here, we can control the morphology, and you can see this rods and the cubics, the thin films. We can control the distribution, of course. So they are very well laid out on this substrate. And we can also control the orientation of this microstructure by using different orientation of this substrate, right? We can use 100, 111, and 110 to grow those epitaxial single crystal structures. So nobody has ever done this before. We were so excited about what we can achieve in this case. And because we can do a lot of different fabrication on this substrate, then we can start to embed the functional layers on top of this electrode. So for example, we can embed those whole electron transport layers to demonstrate some functional device. In this case, you can see we stack a whole bunch of different layers on top of each other, and eventually we're able to grow this crystal on top of these function layers. And the nice thing is that when these single crystals grow out of these holes, they can grow both vertically and laterally. And when they grow laterally, they can form those nice conformal contacts with these underlying functional layers. And after you sprinkle some dielectric layer and do some dry etching, then you can deposit top electrode, and you can show a single crystal light emitting diode in this case. So on the left-hand side are these band alignment, band diagram of these light emitting diodes. And on the right-hand side are some images, optical images, showing this high resolution, high quality light emitting diode based on this patent hybrid highlight perovskites we can achieve. So this is like a very powerful platform. Once we can do architectural growth, once we can do microfabrication on these perovskites, then we can demonstrate a lot of very powerful things. Say, for example, one thing we looked into is strain engineering. Why strain engineering? Strain has been used very widely in industry to tune the carrier dynamics of these semiconductors, right? So what you're looking at here are a series of images showing these single crystal thin films of alpha FAPI. We can grow on a range of substrates, single crystal substrates we can tune. So you can see here, when we tune the composition of this perovskite substrates, the lattice structure change, and also there's a band gap changes. So that is reflected by the color of this substrate. That's because of the absorption is different, right? So we keep, the architectural thin film the same. Then that means this architectural thin film will experience different amount of strain on top of these substrates. So you can see this is our XRD result. When we increase the amount of this chlorine in these substrates, the lattice constant becomes smaller and smaller. Then that means the strain, the compressive strain in this alpha FAPI become larger and larger. So this negative sign denotes a compressive sign in this case. And this compressive strain is also reflected by this Raman spectroscopy we can collect. As you can probably imagine, when we increase the compressive strain from 0 all the way up to 2.4%, the cubic alpha FAPI become more and more tetragonal because it's in-plane compressive. So outer plane is tensile, right? So it become more and more tetragonal. Then it loses its symmetry, then become more and more Raman active. That's why the peak intensity is higher when we increase the compressive strain magnitude. Another very interesting phenomenon we can see is that when the compressive strain is larger than a threshold, the Raman peak split into two peaks. And that is can be explained by this loss of symmetry as well. As you can probably imagine, this in-plane vibration of this lead iodine vibration is going to be different from this lead iodine vibration outer plane, right? Because of different bond lengths. So that's why you have now two peaks instead of one peak when this strain is becoming larger. The major function of this strain is to tune the carrier dynamics of the semiconductors. So this is a simulation by DFT showing that the result shows that when we increase the amount of strain from 0 all the way up to compressive minus 3%, this is like a tensile strain. The effective mass of electrons does not change much. However, the electron, the whole mass degrades gradually. Then that means when we increase the strain from 0 all the way to 3%, the whole mobility becomes larger and larger, right? So this is like by simulation, monotonic decrease. However, in our experiment is very different from this simulation. In our experiment, the result shows that the mobility gradually increase to a certain amount when the strain is about 1.2%, and then gradually decrease. So this is very different from this simulation. And this can be explained by a competing effect from this strain enhancement and also this strain-induced defect that will create more scattering when the strain magnitude is larger, right? So as you can see, as you can imagine, when the compressive strain is larger, then there will be more and more dislocations generated at the interface between the epitaxial thin film and the substrate. So that dislocation will, gradually kill some of this carrier transport. That's why we have a maximum value, a sweet spot at around 1.2%. So this is the result measured by this Hall effect, and this is the result measured by the time of flight. So they show a similar trend with a maximum value of around 1.2%, but they have a different absolute numbers because of a different device structures we use in experiment and also different measurement setup. So as you probably know, a major challenge with this perovskite is that it's metastable. That means it will easily phase change or easily decompose in air in ambient environment in a very short amount of time. This is what also we observe in our experiment. For the case of alpha FAPI, as you can see here, when you first grow them, it looks black because it's alpha FAPI. And after about 1 day, within 24 hours, it decomposes quickly into this yellow phase delta FAPI. And this delta FAPI is less interesting compared to this alpha FAPI because of the reduced carrier transport properties. Surprisingly, under this compressive strain, this alpha FAPI the lifetime of this alpha FAPI can be extended as long as almost 1 year. And this surprising enhancement can be explained by two factors, we think. The major factor is that this epitaxial relationship actually clamp those epitaxial thin film on the substrate by this strong covalent chemical bond at the interface. So as you probably know, phase change will induce those bond breaking at the interface. So there's a strong interfacial chemical bond actually add another layer of barrier that prevents those alpha FAPI from decomposition. So this is a major driving force, a major force that holds that is stabilize this alpha FAPI. The second reason is that this alpha FAPI intrinsically has some tensile strain built in the lattice. So this compressive strain will annihilate some of this tensile strain and make this thin film a little bit more stable. So this enhanced stability is also confirmed by the XRD and also Raman spectroscopy. So these thin films can grow on top of an epitaxial substrate, right? So how can we transfer them? How can we remove them from a rigid substrate and transfer them onto a flexible, stretchable substrate so that we can build all kinds of soft electronic device? In the case of silicon and arsenide, they can be like transferred, they can be undercut, they can be lifted off by many ways, right? Control the undercut ways using these advanced microfabrication approaches. So how can we do with those perovskites, right? Because they are so sensitive to water, right? They decompose. So my group invented an approach that allows us to grow those epitaxial thin films and then transfer them onto an arbitrary substrate. And this result has not been published, and this is also my first time to present this in a public scenario like this. So what you're looking at here are a series of steps we use to grow and transfer this thin film. So we have those patterned bulk single crystal, and we have those masks on top of it. These masks have those defined holes where you want to grow those single crystal perovskites. And when they grow and they fill those holes, and then gradually they grow out both laterally and vertically. And as time goes by, they gradually merge into a single crystal layer of thin film. By controlling the growth parameters such as the precursor solution, concentration, growth temperature, and so on and so forth, you can control the thickness of this thin film. And this is very critical. I'm going to explain to you later. And then after that, you peel off the mask layer, and then there's a single crystal thin film is then peeled off. So on the right here are series of images showing each step of this growth process. So what you're looking at here are some images showing this thin film of a 1 centimeter by 1 centimeter thin film with a thickness of around 2 micron, and the thinness we can grow is about 600 nanometer in thickness. And after the thin film is transferred on a curved PDMS substrate, and the thin film can be on a large scale. In this case, it's about 5 by 5 centimeter with a thickness of around 20 micron on a copper foil. So this can be scalable to even larger area if we have this large single crystal as the substrate. Why thickness is critical, right? So for 2 reasons. The first reason is that we have to control the carrier transport properties and also the light absorption in this device. So as you probably know, when this material thickness becomes thicker, then it can absorb more light. Then the device performance will be higher, right? You have more energy incoming. The second, and also you have to balance the transport. You have to balance transport because when this material is thicker, the carriers, the free carriers, will have a harder time to be collected. They will recombine before they can get collected, right? So if the material is too thick, so we have to make a trade-off between the thickness, between this light absorption and the collection efficiency. And in our experiment, we find out that the sweet spot is about 2 micron. 2 micron can give us this best external quantum efficiency and also the best solar cell efficiency in this the JV curve. The second reason for this thickness control is to enhance the flexibility. So this is also what I learned in Professor John Rogers' group. As you can see here, this conventional mechanics, the peak strain in this same film is linearly proportional to its thickness. Then that means the thinner the material, the smaller the peak strain. Then that means the more flexible it becomes, right? So here are some simulation by finite element analysis showing a bending curvature of around 2.4 millimeter of a thin film that has a thickness of around 20 micrometers. Here on the right-hand side are the series of images showing how bendable this thin film is, right? Beyond the 2.5 millimeter, then you have this fracture showing up. A very nice technique we can apply in this growth process is that we can tune the bend gap of this thin film into a graded band gap structure. Okay, how can we do this, right? So as you can see here on the left-hand side, on the left-hand image is the fluorescent image showing the thin film with graded band gap growing on a substrate of this MAPBBR3. So we use this material as a substrate. So this is a bulk substrate. And then we first flow those solution with equal amount of lead and tin inside. Okay, so this have this equal amount of this lead and tin, and then grow into the thin film. And then gradually we reduce the amount of the tin solution. So that will be reflected by the thin film composition we can grow in this material, right? And then finally, we use pure lead without any tin. So in this case, during the single crystal process, the composition of this thin film is gradually changed as a function of thickness from the bottom to the top, right? So this is the fluorescent image. As you can see here, this is red, this is the infrared. That's why it shows dark here, because you cannot see this infrared image. And this is like a large band, this is like very small band gap, this large band gap on the top. So this image on the right showing the intact structure of this thin film. You do not see any structural interface because the entire thin film is a monolithic single crystal without any interface that would otherwise reduce the carrier transport mobility. So what's the advantage of this graded band gap? So this is a conventional flat single material, single composition band gap. And this is a graded band gap structure in this case. So this graded band gap has two advantages. One is this enhanced carrier collection efficiency. So this tilted band gap just mimic this built-in potential of a PN junction, right? So this built-in potential can enhance this carrier drifting, so that it can reduce the carrier recombination in this built-in potential region. And this tilted band gap edge can do a similar thing, right? So the second advantage of this tilted band gap is that it allows us to enhance absorption of this light. So as you probably know, the shorter wavelengths of light has a less penetration depth, and the people normally use the tandem solar cell to enhance this absorption. In our case, we can merge all of those tandem solar cells into one single layer of absorber here. This small band gap is on the top to absorb this long wavelength light, and this large band gap material at the bottom to absorb this large, shorter wavelength light, right? So this graded band gap is reflected by this absorption spectroscopy. You can see here this band gap gradually change as we increase the time, and this embedded schematics showing these graded band gap structures. And this graded band gap structure has been demonstrated in a solar cell, and this device shows a certified efficiency of around 18.9%, which is higher than the solar cell efficiency using a uniform composition material. So finally, we were able to demonstrate a flexible single crystal high performance solar cell that can be integrated with the skin. And this is like the image of the device on the skin, and the inset here showing this cross-section structure showing these multi-layered devices. You can see there's a single crystal perovskite. And this device is scalable to large area and is flexible. And also it shows enhanced stability, because in this case, a single crystal devices does not have these green boundaries, which normally show in this hard crystal case, that will enhance this transport of this moisture molecules and oxygen molecules and reduce lifetime, right? So this is the first time for us to show a single crystal large area solar cell in this case. And this device can be bend release for cycling over hundreds of times. And it is stable when it is bent to around 3 millimeter in bending radius. And if you keep bending them, then the device will collapse due to this material delamination at the interface. So reducing the material dimension is one strategy to make these devices flexible. But what if you have some material that is not small, right? It's very bulky. And what if you do not want to reduce dimension, right? So so in this case, we have to use a structure called the island bridge. So what you're looking at here is a simulation video showing a 2x2 array of islands interconnected by those wavy bridges. And you can see that during this stretching, releasing process, those islands remain intact, remain still. So in this case, we can integrate those rigid functional components on these islands, and those bridges will absorb this tensile strain. And those non-uniform color indicate those peak strain in this entire process. And we have to make sure that this strain is smaller than the failure strain, the fracture strain, before before we do the fabrication. And we will be able to encapsulate this entire structure using some soft polymers or liquid to enhance the stability, the bending behavior of these bridges. And there are some criteria to select those encapsulation material. So we applied this island bridge structure to a variety of different kinds of devices. So what you're looking at here is a stretchable lithium battery. So as you can see here, we decompose those continuous cathode and anode into an array of those cathode and anodes and you can see here, this is like a 10 by 10 array, and each one of the dot corresponds to one small cathode island and anode island. So what I want you to notice is this the brightness of the LED. As you can see here, when we stretch the battery, the brightness of the LED does not change at all, which shows this device does not change its performance when we deform it, right? So this is like one clear advantage of this design. And we also can screen print different kinds of catalysts onto the island bridge structures. And here is an exploded view of this device. And this is in collaboration with our collaborator Joe Wang at the UC San Diego. He selected, optimized the performance of the ink. So this is an in vitro video showing how we can harvest the glucose solution to generate this power for powering LED. And at the bottom here is an in vitro video showing the student actually use one of the device, embedding this device underneath a wristband and do some exercise in the gym. The sweat the student produce can be sufficient to power an LED and associated electronics without any battery or external power supply. And this is the platform technology. We can screen print different kinds of inks onto these islands to target different biomarkers on the human body, specifically in this sweat and in interstitial fluid. This is also in collaboration with my colleague Joe Wang, and the device is very soft, can be delaminated, can be deformed with the human skin. And by selecting different catalysts, we can use this device to target different analytes. For example, this explosive material and the biomarkers, right? The most exciting thing for this technique is that it allows us to stand on the shoulder of this existing developments of this industry, right? So what does that mean? That means we can use those, we can leverage those highly integrated electronic components as a building block to make this stretchable device. So what you're looking at here is a fully functional, fully integrated wearable patch that can realize 3 functions: wireless energy harvesting, local data processing, and wireless communication with about 14 chips, right? So they are highly integrated, highly functional. So this is the central circuit hub. And on the 2 sides are these 2 electrodes that can be laminated on the human body to collect those local field potentials, electrophysiology. And what does this device do? So this is live video showing how the device works. So if you put this device on the chest and stick in a coil, okay, so we have to stick in coil to deliver the power. It's wireless energy harvesting, but the working distance is limited to a few millimeters. We have like a second generation of this device that has a longer working distance. So when the device is powered up, it can connect this EKG signal and the wireless transmit to your laptop, to your cell phone, to the cloud. So what you're looking at here, the raw data, we did not do any post-processing here. So you can already identify this characteristic peaks as you would expect to see in this high quality hospital environment. And the baseline shifted for the first few seconds because we have a capacitor in the circuit. We have to charge our capacitors first before the baseline becomes stable. So wearables is still emerging. It can realize very powerful functions, but it's still pretty mature in comparison to what we can achieve in the industry. So what you're looking at here is a typical result that the people can achieve in industry is 80-layer printed circuit board, 80-layer PCB, right? So it's like a 3D matrix in this case. The enabling technology for this 80-layer PCB is that it has a structure called VIA, vertical interconnect access VIA structure. So what does this VIA do is that it connects those different layers and provides electricity and signal between those layers. It's like the elevators in a tall building. Elevators provides people and the resources between those different layers of buildings, right? So VIAs do a similar thing. So this is actually a 3D matrix, complex interconnected matrix on this PCB board. The challenge is that
vias can only be realized on these rigid silicon arsenide substrates. It's very, very difficult to realize to achieve via structures on these stretchy elastomer silicon-based substrates. So my group invented a technique by coupling a laser ablation to drill vias into these silicon-based elastomer substrates. So we use the different dyes to dope those these silicon elastomers to maximize this absorption, and then we tune the pulse energy and the pulse repetitive cycle. So eventually, we were able to selectively remove any kind of material in the presence of any others. So at the bottom here are the images showing 3 typical via structures. Through via connecting all of the layers, right? So this is the via, these are the 4 layers of the copper circuit, and buried via connecting some layers in the middle, and the blind via connecting some of these layers at the top, right? So with those enabling via structures, then we can start to build this stretchable device layer by layer. So what you're looking at here is a schematic device showing a 4-layer stretchable device. This is a schematic. This is the first proof of concept. But this device, but this technique can be scaled up to more layers if there is a need. So in each layer, we have these functional components, strain sensors, temperature sensors, circuit components, and antennas, so on and so forth. And this is the first demonstration of this multi-layered stretchable device. And what you're looking at here on the right-hand side are the series of images showing how we do the fabrication layer by layer. And you do this first layer, and then you sprinkle a insulating silicone elastomer, and then use laser to drill those via holes, and then screen print those solder paste, followed by transfer printing the second layer, and then you reflow everything in the thermal oven, then entire first and second layer are bonded together. So using a similar approach, we can build the third and fourth layers. So how does this device deform, right? You can stretch it to 35% horizontally and vertically 50%. And because of the robust mechanical design and fabrication, we remove the strain and recover to its original shape, right? So this is device can be cycled to like over 1,000 cycles. And how does each layer of this device deform? And this, as I said, this was like the first demonstration of this multi-layered stretchable device in the literature. We want to examine like how each one of the layers deform. And then we use X-ray. X-ray can penetrate a lot of stuff. And this is XCT, and this is like before stretching, after it stretches 35%, each one of these interconnects stretch out uniformly, except these like areas, where these chips have this like a clamping effect, right? So we have to carefully design to minimize the strain between this rigid chip and the soft surrounding matrix. So what I want you to notice is this cross-section of the vias, right? So this is a typical via connecting the first and second layer before stretching, and after stretching. You can see it barely deforms, clearly showing this mechanical robustness of these via structures. So what does this device do? This is a final question we have to answer. And this via structure does not only allow us to integrate more functions, more components within limited footprint. It also enables new challenges, functions that are very difficult to realize with these single layer designs. So the function we realize is 8 channel of sensing of different signals with a wireless Bluetooth 10 meter working distance in this case. And the 8 channels of sensing are 6 channels of accelerometer and 2 channels of goniometer. And there's a breathing, strain sensor for breathing detection, inhale and exhale, and this electrophysiology sensing, right? This EMG when you put this device on your arm, and this EOG, eye gazing angle when you put this device on the side head. So what do we use those signals for? We can use them for wireless monitoring and fitness monitoring, no problem. But we also use those signals to control a robotic arm, to control a prosthetic arm, right? So this is 6 channels of signals, with each one of the channel of signal to control 1 degree of freedom, 1 motor in this robotic arm here, right? So the only interface between the real hand and this robotic hand is this wireless patch here. This was like the first multimodal high degree of freedom control between the real hand and the robotic hand in the literature. So wearable device is so powerful. I'm sure you can list a million kinds of different sensing functions in the literature. So here's a brief summary is what wearable devices, stretchable devices can do, right? It can basically categorize into two groups: physical signals and chemical signals, right? So I'm not going to go through each one of them, but the key message is that these signals all have one limitation. The limitation of the existing stretchable device is that it can only sense signals on the skin surface or very shallow into the skin surface, right? Say, for example, if you use LED, if you use LED, either green or red or infrared, LED can only penetrate very shallow depths into human body, limit to a few millimeters, right? So all of these wearable devices can only capture signals within a depth of a few millimeters, right? There are a lot of more signals beyond a few millimeters. What do we do? What do we do with these wearables to capture those signals in your central organs? So my group into monitoring those central organs into wearable device using ultrasound, right? As you probably know, ultrasound has a high penetration depth into the human body and is also biocompatible. It's safe to the human tissue, right? It has a well-tracked record of this safety, regulation, approval policies, right? So on and so forth. So using a wearable device, using a wearable ultrasound device, we will be able to continuously, non-invasively monitor those central organs. Nobody has ever done this before in the literature. So what you're looking at here is a schematic design showing a stretchable ultrasonic patch with about a 10 by 10 array of those ultrasonic transducers. And this is exploded view of these laser structures. And we control each one of these transducers with over 100 electrodes, right? So this is what we are good at. And at the bottom here are the images showing how soft, how compliant those ultrasound devices is. It can be bendable, it can be stretchable, it can be stretchable with all kinds of mixed mode of deformation. So these are the characterization curves data showing the electromechanical functions of these transducers. Because we use those high performance 1-3 composite as the building block, so it has a state of art in performance. And because of this isolation effect of these transducers using this ecoflex in between them, right? So it shows this very reproducible frequency, resonant frequencies. It also has a minimum crosstalk in between them. And we have also done this simulation showing the mechanical robustness. And after we stretch this device from 0% to 40%, the electromechanical coupling does not get infected, clearly showing the mechanical robustness of the device. What do we use this device for, right? We first apply this device to imaging. And this is like showing images showing how the device image on a flat surface, concave and convex surfaces, right? So this is the defect embedded in this material. Why is this interesting? This can be used for non-destructive examination of these airplanes, cars, buildings, bridges, right? Otherwise, you will have to disassemble those complex infrastructure and immerse them in some liquid environment to do this imaging, right? So with this soft ultrasonic probe, we will be able to do this imaging in situ without disassemble this material. And this is simulation showing how this ultrasonic wave propagate inside this material. And these are the data we can collect. And after we know the ultrasonic speed in this infrastructure, then we can calculate, we can image, we can know exactly the location of the defect. We went a step further by doing this 3D imaging using a 2D array. And this is like this showing two defects within an aluminum block. This is schematic design, and this is the imaging result in 3D, and this is the imaging result in 2D, showing this view orientation along different directions, which match to this design perfectly. I would say the most exciting thing of this wearable ultrasonic device is that it can be used to monitor a lot of vital signs in the human body, right? This is like how soft this device is when we laminate on the human body. When we move around, it does not delaminate, clearly showing the minimal mechanical loading on the human body. How deep the ultrasonic can penetrate? With a transducer size of around 0.9 millimeter by 0.9 millimeter at a frequency of 3.5 megahertz, it can penetrate of about 40 millimeter. And this penetration depth is tunable by the size, the frequency, and the power, right? In our published results, we can penetrate of about 14 centimeter inside the human bodies, and that means we can have access to almost every part of a human organ. What do we do, right? What's the physiological signal we can sense? The first thing we looked at was like a blood pressure. Why blood pressure? As you probably don't know, hypertension, reduced cardiovascular disease is the #1 risk factor that kills more people than all cancers combined, right? It's a silent killer. And there are a lot of devices on the market to monitor the blood pressure. Cuff is the most common one, but it has limitations of being discrete. That means it can only record the systolic and diastolic blood pressure values. It only give you a snapshot of a continuous movie, right? As you probably know, blood pressure is a ever-changing parameter as a function of your emotion, your stress level, your body posture, your room environment, your food and medicine, exercise, so on and so forth, right? So you need a device that can capture those continuous blood pressure waveform, rather than just 2 snapshots. And also, cuff can only record the peripheral blood pressure, which means it can only record these values in the wrist and in the arm. What's really critical, what really kills people, are the blood pressure values in your central organs, in your heart, in your brain, in your lung, in your kidney, so on and so forth. PPG is another device that people typically use. Again, it can only sense the peripheral blood pressure, and it's very prone to artifacts, the skin color, the moisture of your skin, and the skin temperature as well. Tonometer is highly operator dependent. It has a steep learning curve, is not very common nowadays. Caster. So this is like a very invasive. This is the clinical gold standard. It can give you a very accurate measurement, but it's too invasive. You do not want to do this measurement every day unless you are critical ill in the ICU environment. So how can we measure blood pressure using a wearable ultrasound patch, right? So this is like schematics showing the working principle. Each one of the transducers can be controlled individually, and an ultrasound beam can be transmitted, and it can be used to illuminate like these blood vessels, and then you will have 2 echoes from these 2 reflections from these 2 walls, anterior wall and posterior wall. By monitoring the distance between those 2 reflections, we are effectively monitor the diameter of the vessel, and by transmitting 5,000 pulses every second into the human body, we can record a waveform of this blood vessel in high temporal resolution, right? 5,000 times every second. How can we transform this vessel diameter into blood pressure? So through a series of well-established equations. So I know it's a Friday night in Beijing right now, so I know everybody is tired. So without sending everybody into sleep, so just highlight 3 important things to get this blood pressure. One thing is that we have to know this vessel diameter. The second thing, we have to know this vessel stiffness. And the third thing is we have to know a baseline, which is the diastolic blood pressure. So the last 2 things can be acquired from a calibration using a cuff. right? So after calibration, then we can get these blood pressure waveforms. So what you're looking at here are these operational data. So we are particularly interested in this blood pressure waveform in the neck, and that's because there are two critical vessels in your neck: carotid artery and this jugular vein, external jugular vein. Those two vessels are directly connected to your heart, right, through your aorta. So they are deemed as these central vessels. So here is the waveform from the carotid artery, and this is from the jugular vein. You can obviously identify a lot of features in this waveform, and those are like abundant information. Each one of these feature in the waveform corresponds to one cardiovascular process in your heart, valve closure, opening, so on and so forth, ventricular squeezing, relax, so on and so forth. So those like abundant information has not been available conventional using non-invasive approaches, right? So this opened up a lot of exciting opportunities for these clinicians to study this pathology and this like etiology of these diseases. And we can not only measure this blood pressure in your neck, but also in your arm, wrist, and foot, so on and so forth. As you can see here, when we monitor the blood pressure at different locations, the pulse pressure becomes higher as you move further away from these central heart positions. That is so-called amplification effect. And we have also done calibration using a tonometer, and they show very well correspondence to each other after calibration. And because of the intimate contact with the human skin, we can do this measurement when we are rotating the arm, right? So this is like a continuous recording. And this is like when the arm is flat and during movement, this is during movement, and when we at a different location here. And you can see here, using a conventional device, when we start to rotate, the measurement get messed up. And we can, then we can start to monitor this blood pressure before and after exercise. You can see the pulse pressure become higher, and also heart rate become higher after exercise, right? This measurement is reproducible, is robust. Within a few weeks, we measure, on the same subject. And because of the conformal contact, this device can enable continuous measurement even without the gel, right? So this enhances the availability of this device. And in our recent development, we can now encode these smart algorithms that allows us to continuously record these blood pressure waveforms in real time. So after publishing our work, this work has attracted a lot of attention. So one thing I want to highlight is that our work was used as a testimony in a congressional hearing. So for those of you who do not know what a congressional hearing is that typically those funding to those agencies, NSF or NIH, is directly from this Congress appropriation. And by the end of this fiscal year, those agency directors will have to report to those congressmen and congresswomen, how they have spent their, funding, right? What are the research outcomes? So here's a video showing a NIH director use our research as a testimony of their extramural research support. So it's very interesting to watch.
I want each of you briefly to, I know it's about resources. If resources were available, though, what is the innovative research that you would like to pursue? Dr. Austin, you just mentioned a piece of this, which is really quite extraordinary in a direction that we can go in. But let me just ask you, where would you like to go? What would you like to pursue?
You're looking at me. Does that mean I should start?
Well, look, okay. I don't have to do it. This is not, it's anybody who wants to go first can go first. Let's go. You go first.
Okay. Well, one of the areas that I'm really excited and passionate about is kind of the idea that current medicine, as it's practiced, takes snapshots, kind of static snapshots. A little bit of blood chemistry here, maybe another year or two after that. An image here, maybe another year or two or 5 after that. blood pressure, even that is not measured very frequently. It's difficult to measure at home. And some of you may know, every time you breathe in and out, your blood pressure changes. We call this dynamics. And the dynamics could be the most important thing about managing your blood pressure. And then you go to the doctor's office and your blood pressure is elevated and they give you medication. Then you go home and then you come back later and they say, well, it's not working. And then you go home and then you come back later. So there's this iterative optimization. Current medicine is practiced at large time intervals. So a big challenge for our community is to come up with better, faster, more accurate, continuous wearable and implantable sensors that are measuring many, many complex things, because we know biology is not simple. And we also know it's quite dynamic. If we can capture the dynamics, every time you eat, your body chemistry goes crazy. How about if we could measure all those things and figure out how to better manage your diabetes and metabolic disease and prevent obesity? What if we could wear this continuous flexible patch that is an ultrasound device that measures blood pressure on a continuous basis? And we can look at what happens when you go to a hearing to your blood pressure. We could follow that with everyone. And how well it's regulated by the medication that you are receiving from your physician. So I think this is the big...
Oops. But you get the gist of this.
Big challenge for us. What it would do is it would extend health span.
Yeah.
So it would prevent disease better. It would give people the power to control what they do and how it impacts their future health. So that's our big challenge.
Thank you.
Hopefully during the past 1 hour or so, I hope I have convinced you that soft electronic device can really adjust some critical unmet needs and holds implications for broad areas of applications. And obviously, this is a multidisciplinary field. I come from a background of chemistry and materials, and we need to work with mechanical engineers for design and simulation, electrical engineers for realizing all kinds of circuit functions, and also biomedical engineers and even clinicians for validating our devices and give us critical, valuable feedback for the next round of iterations. And I've showed you 3 messages. One is that we demonstrated a new approach for fabricating this large area single crystal organic inorganic highlight perovskites, which opened up a lot of opportunities in the community. And we also demonstrated enabling technology for building multi-layered stretchable device, which does not only allow you to integrate more functions, but also enable new functions that are challenging for these single-layer designs. And the wearable ultrasound device opened up a new sensing third dimension for the conventional stretchable device that has a lot of applications for human health monitoring. So finally, I want to conclude by acknowledging my students and postdocs. I'm learning from them every day, and also my critical collaborators. Without their support, I cannot accomplish those work, and also the support from these funding agencies. The size of the logo is roughly proportional to the amount of funding I receive from them. And finally, I do want to make an announcement that my group is looking for motivated students and postdocs with a background in ultrasound. And it can be broadly defined from materials fabrication to hardware control system designs, and even like this signal imaging algorithm development. If you're interested, please send me to your send your CV to me. My contact information is here. So this is like the beautiful campus. This is where our building is, and this is the Pacific Ocean. And on the other side of the coast is the Beijing. With that, thank you very much, and I'll be happy to take any questions.
Okay, great, Sheng. Yeah, it's a very nice talk. Actually, we came to the question part, and I think you delivered really great message, and everyone was looking for that. We have really large numbers now. So now the questions is very hot. So I got the questions first to you. And the first one is, dear Professor Yu, great work. Is that possible to use as OI substrate? Maybe it can simplify the process or make it more suitable to integrate it with industry fabrication. Comments on this?
Yes, that's a good question. for the first few examples I gave, like the silicon ribbon control the buckled in silicon ribbon on the stretchable substrate, that was made out of SiO wafers, and that was work when I was a postdoc in Professor John Rogers' School. So the challenge here is how can you make an equivalent SOI wafer for perovskite, right? SOI wafer, what does S mean? S stands for silicon, right? Can you make POI wafer, perovskite on insulator, wafer, something like that? So my group invented such an approach that allows you to grow those epitaxial thin films on a well-defined, perovskite substrate itself. So that is similar to this SOI concept. So that's a good question.
Okay, great. Yeah, I think, if you can go to this kind of direction, that's more important for everyone, can follow up, right? Yeah. Okay, yeah, so this was second question is Professor Yu, thanks for the wonderful talk. For the multi-layer with wear, yeah, do you need any special coating on the surface to avoid crosstalk or interference on the different layers?
Well, that's another good question. Right now, we use a silicon elastomer as the insulating layer material between each layers. And as you know, silicon elastomer has a very high breakdown voltage, which is sufficient to isolate any electrical crosstalk between them, right? And as a next step, we need to further reduce the thickness of this silicon elastomer so that the overall, form factor, the thickness will be smaller. And that is still under development. But one criteria is that it has to be stretchable, so that it does not compromise the overall compliance of the device.
Okay, so a follow-up question is now how thick the thickness, how thin it can be till now?
Well, yes, for the device, for the 4-layered stretchable device we demonstrated, is about 1 millimeter in thickness. And that is largely dependent on the trick we use, the commercial off-the-shelf components we use. And the thickest is 1 millimeter. So that sets up the bar, the overall thickness of the device. If we can somehow reduce the thickness of the commercial off-the-shelf components, we can make the entire device to be very thin, like a few hundred micrometers, no problem. Even below 100 micron, truly like a secondary electronic skin. The challenge is how can we get this components, integrated components into a and integrate them into this multi-layered geometry. So that is the next challenge we are working on right now. Yeah.
Okay, great. So yeah, the third question is how about the power consumption of your multimedia system? And you use integrated biofuel cell battery as power source?
Yes, power source is a grand challenge in the field. I'm sure, Paul, I saw Paul was smiling. I'm sure he has a lot of understanding as well. So in our case, our innovation is a 4-layered, stretchable device. So we used a battery in this case on board to power the device. We can use the biofuel cell, but always the challenge